Assalamu alaikum and greetings. So in the last couple of lectures we talked about Fourier transform, the impulse function, some properties of Fourier transform. Now we move towards discrete Fourier transform. Now Fourier transform is really a tool that helps transform a signal from time domain to the frequency domain. And if we take a discrete signal and feed it into the Fourier transform, it's called a discrete time Fourier transform. Now from the DTFT we evolved another tool which is called discrete Fourier transform. Now, well, you could say that the only thing we are doing from DTFT to DFT, or discrete time Fourier transform, to discrete Fourier transform is remove this time, and that's really what we are doing here. But this lecture will explain to you, well, that's not entirely the case. And once you've talked about discrete Fourier transform, we will move into two-dimensional discrete Fourier transform, because all your images are two-dimensional in nature. Well, let's start with the definition of discrete time Fourier transform. Now, discrete time Fourier transform, this is the definition. So consider a causal signal. It doesn't have to be a causal signal. For a non-causal signal, the summation will range from negative infinity to positive infinity. Here, because the signal starts from 0, the summation starts from 0 to infinity. Now in this particular instance, you have this discrete signal. Again, it's a discrete signal, that is why we have a summation. That's why we have a summation here, because it is a discrete signal. And then we take we find out we convert it into Fourier domain or frequency domain, and this is what we get. So what we're really doing, and this is important to understand, we're converting a discrete time signal n into omega, which is in frequency domain. Now omega is the angular frequency. So omega ranges from 0 to 2 pi. It is an angular frequency. So here it's defined very similar to the Z transform. So you have this angular frequency. The signal omega ranges from, it starts from the distance from the radius here from the origin is 1. That's why. And then the angle starts from 0 up until, this is pi, which is 180 degrees. This is 2 pi, which is 360 degrees. And then it is continuous. Notice that omega is in fact continuous over this domain 0 to 2 pi. Moreover, it is periodic. Right? Once it rotates once, it rotates again within the same component. And that's something important to understand, is that your omega that you're converting, technically this is what you're doing. You're converting a discrete signal into a Fourier, or its frequency transformation is a signal defined in omega, which is continuous between 0 to 2 pi, and it is periodic. And that's an extremely important principle, that you're converting a discrete signal in time domain. Doesn't have to be periodic. It's a discrete signal in time domain. It's a discrete aperiodic signal in time domain into a frequency transformation where omega is continuous and periodic. So in DTFT you have a continuous and periodic waveform in frequency domain, where omega ranges from 0 to 2 pi, and this is sometimes referred to as the digital frequency. Now compare that with the Fourier transform. A lot of the books in fact don't use this omega small omega, they use this capital omega sign. Over there, however, the signal, well, it is continuous. It could be periodic. It does not have to be periodic. It could be aperiodic. But it ranges from minus infinity to infinity. So that's one important differentiation that you should understand. That when you take the Fourier transform, you get a continuous waveform, but it is an angular frequency. And this is called angular frequency. This is sometimes referred to as digital frequency. Now, extending to that, the inverse DTFT, or the inverse discrete Fourier transform, notice you changed it to a continuous, you took a discrete signal, you applied DTFT and you changed it to a continuous and periodic waveform in frequency domain where omega ranged from 0 to 2 pi. Now, because this is continuous and periodic, if you have to take the inverse of this so that you can get back x of n, the first thing you have to understand, this is continuous. So the summation changes to an integration. The summation changes to integration. Secondly, this is a periodic waveform. So you're taking it over one period from 0 to 2 pi and you're dividing it by that very time period. The other obvious thing is, this is e raised power plus j omega n. Over here you notice this is e raised power minus j omega n. So this is your inverse discrete Fourier transform. Inverse discrete time Fourier transform. Obviously the integration is with respect to omega because you are integrating it in omega domain or the frequency domain. Now moving from here, now what about the discrete Fourier transform? Well, these are some example signals and their transformations. So if you have an aperiodic signal in time domain, you're going to take the Fourier transform. If you have an aperiodic signal, if you have a periodic signal in time domain, you're going to take the Fourier series. What we just did right now was the discrete time Fourier transform. Now in a discrete time Fourier transform, the input signal is discrete in nature. That's why you see these dots. This signal is defined at certain instances in time domain. But notice you have an aperiodic discrete signal. Let me go back here. You have an aperiodic discrete signal. Therefore, the transformation is known as discrete time Fourier transform. But at the same time, if you have a periodic discrete signal, then what you take is a discrete Fourier transform. So let's see how this behaves. This is your definition for a discrete Fourier transform. Now notice what you're doing. Number one, you're taking a discrete signal which is x of n. It is periodic, so it has a period 0 to n minus 1. So the first thing that you have to understand, this is a discrete signal, so you'll have a summation here. Secondly, this, because it's periodic, you're going to define it over one time period. And then what you're going to do is you take this summation and what you get is a discrete and periodic transformation in frequency domain where the frequency components are shown by k and it also ranges from 0 to n minus 1. In other words, what is very different from the discrete time Fourier transform in which you obtained a continuous waveform which was periodic in omega domain, here you're getting a discrete waveform. It is still periodic, but it is discrete in nature. That's why you have x of k. Therefore, when you take the inverse of this, again you have a summation. Summation because it is discrete in nature and defined over, this is n minus 1. It's defined over the same time period. So this is the inverse discrete Fourier transform. Now, The first difference between discrete time Fourier transform, let's look at the common things. Well, in discrete time Fourier transform and discrete Fourier transform, the input is discrete. In both cases, the input is discrete. In one case, the signal input is aperiodic. In the other case, it is periodic in nature. The third case is, once you take the discrete time Fourier transform, your signal in frequency domain is periodic, where there is an angular frequency omega which ranges from 0 to 2 pi. In this case, the frequency transform is periodic, but the signal is no more continuous. It is discrete in nature. So, now that you understand what is discrete Fourier transform, this is the formula. The other thing is, we need now to extend this, because this course is biomedical signal and image processing. Now we need to move into images. Now images, well, they are defined in both X and Y domain. An image is a signal which is defined in two dimensions. One is X and other is Y. So if we extend the same principle of one-dimensional discrete Fourier transform to two-dimensional discrete Fourier transform, the extension is straightforward. In fact, let's look at this transformation. Well, for instance, the signal is both defined in X and Y domain. Here, notice it's e raised to minus j2 pi n over n times k. Here it is again minus j minus j2 pi k n over y. Rather than n, he's taking y because the signal is in y domain. So this is a straightforward extension. Okay, the inverse two-dimensional discrete Fourier transform is an extension, is a straightforward extension of the single, to the single as well. Now, as an interesting note, there is a two-dimensional cosine transform as well, but we are not going to discuss that right now. But the whole point is that you have a signal which is two-dimensional in nature. It is an image. It is defined over X and Y coordinates. So how do you take the Fourier transform of that? Now, for a discrete Fourier transform, all you're doing is, again, you're converting a signal in discrete domain, which is periodic, into its equivalent. What you're really trying to do is, what are the cosine, the sum of the cosine and the sine, what is the sum of the sine and cosine components that together make this up? Now, obviously, having an imaginary component and having a real component means it's, that's the whole point. It's somehow circling around this domain, as is seen over here. Now, but going back to this, the two-dimensional looks like this. This is a mere extension to what we've already seen. The whole point is the following. Now, if you look at these images, these are some images. This is your typical X-ray. This is a microscopic image. Now, when I look at this image, the high frequency, and this is where the principle comes in, the high frequency are your boundaries, where the signal changes from a darker image to suddenly a lighter image. In other words, there's a huge frequency component at all the boundaries. But once you enter that boundary, the shade is pretty much the same. It's more or less the same. It means once you enter the boundary of a particular region, as for instance this X-ray, once you enter this boundary, the color doesn't change much. The gray shades, this is a gray shade, sorry. So the gray shade doesn't change much. So your lower frequency components is what is inside a particular structure, because the shade doesn't change much when you're moving from one end to the other end. But the high frequency components are the boundaries of different organelles or structures. Okay? That was it for today. Inshallah ta'ala, next time we're going to talk about image filtering, enhancement and restoration. Thank you very much and have a good day. Assalamu alaikum.